Okay, any questions before we get started on homework? Okay. If you look, if you've noticed, I've extended the 4.4 homework to Wednesday since I won't be finishing it until today. So 4.4 is due Wednesday. 4.5 I will cover tomorrow and Wednesday. That'll be due on Friday, and the first exam is this coming Friday. And that'll just cover Chapter 4, Sections 4.1 through 4.5. I have added more suggested textbook exercises for Section 4.4 onto my math lab under the Announcements tab. I will make sure I get some problems for 4.5 posted later this afternoon. Also, I'll try and get those homeworks 4.3 graded and back today. Okay. Anybody that does not have a 4.4 handout? Anybody need a 4.4 handout? Okay.
I do.
You got one, Claire? Yeah. Okay. All right. So, as I said, from now on, I'll probably get some sort of tripod so I don't have to roll this card up here every time. And it might be obstructing some of your views, so I apologize for that for the next couple of days. But I'm just going to record these class sessions and get them posted on Canvas, or I'll get them posted somewhere and let everybody know. Just let me know on how the quality is. Hopefully the sound comes through very well. Only issue I've noticed, I came in here this morning and there's a little bit of glare coming from the lights on the board. So I'm going to try my best to use fresh, bold colored markers. So hopefully that makes everything clear and easy to read. Okay, so first of all, I just want to remind everybody about the domain and ranges of secant, cosecant, and cotangent before we get started. So first of all, I'll come over here. Remember, secant theta was 1 over cosine theta. Cosecant theta is defined to be 1 over sine theta, and cotangent of theta is supposed to be, and hold on, I guess I'll stick with the book. Every once in a while you'll see people put parentheses around their inputs for a trig function. When it's clear though, if you just have a single input, you can just write cotangent of the input, sine of the input, whatever it is. But cotangent theta is defined to be 1 over tangent theta. Here the period of secant is 2 pi. The period of cosecant is also 2 pi. That comes from the period of sine and cosine. And the period of cotangent is also pi, just like it is for tangent. So there's your 3 reciprocal trig functions. I'll make a quick table. And we will write down the domains and ranges again of these. Secant theta is defined anywhere cosine of theta is non-zero, which happens at pi over 2 plus or minus any multiple of pi. So the domain here would be the set of all angles theta such that the angles are not equal to pi over 2 plus any multiple of pi. And that's where k is an integer. In the range, I think, was negative infinity to negative 1 union 1 to infinity. Okay. Cosecant theta is defined wherever sine is non-zero, and sine is 0 for any multiple of pi. So you can go look at the graph of sine of theta. You'll see it crosses the horizontal axis at any multiple of pi. Okay, so things not in the domain of cosecant are any of those multiples of pi. And then you have the same range as secant. So less than or equal to negative 1 or greater than or equal to 1. And then cotangent has the same domain as cosecant. Anywhere that, so you can plug any angle into cotangent as long as it's not a multiple of pi. And the range, just like for tangent, is still all real numbers. Okay. And then I think what we did is on Friday we left off, if you want to graph a transformation, especially of secant or cosecant, you first apply the same transformations to the graph of the reciprocal, of the corresponding reciprocal function. If I want to graph a transformation of secant, I apply the same transformations to cosine of theta. Anywhere you cross the midline is where you have vertical asymptotes, and then the transformed secant graph will always open upward from a maximum value and open downward from a minimum value. Okay. Today we're going to do example 3, so we're going to, by hand, find a domain and range of a transformed cosecant graph. So we're going to find the domain of the function f of theta, which is 3 cosecant pi over 3 theta plus 4. So, sorry, domain and range. So we want to find the domain and range of this function. And then how about just for practice, we'll sketch a graph too, just to go through that process one more time. Okay. So let's take care of the domain first. I want to focus on this pi over 3 theta. That is my input. Okay, if you like, you can even just say pi over 3 theta is some angle beta. Okay, so we always think of our inputs on these trig functions as angles. Okay, so if you like, we'll call pi over 3 theta beta. And since beta is being plugged into cosecant, our domain is going to be all the betas, so that beta is not equal to a multiple of pi. Okay, so we can start out, beta cannot equal k pi, where k is an integer. But then you have to remember that I made a substitution. Okay, beta was really pi over 3 theta. So this implies, so our input's really beta, which is pi over 3 theta. Those cannot be any multiple of pi, where k is an integer. Okay. So I'm taking my varied input, pi over 3 theta. We're saying that cannot be a multiple of pi. And then the last thing I need to do is solve for theta. Right? Theta is really the input of our overall function. But we look over here, we just know that pi thirds theta cannot equal k pi. Now solve this for theta. Theta cannot equal, if you multiply both sides by 3 over pi, you'll get that theta cannot be a multiple of 3. Okay, so 3 over pi times k pi just leaves you with 3k, where k is not where k is an integer. And then finally, the domain then is comprised of all such thetas, such that theta is not equal to 3k, where k is an integer. And that would be your set that comprises the domain. Okay, so you always take your varied input and say that it cannot equal, in this case, since we're dealing with cosecant, our input cannot equal a multiple of pi, so it can equal k pi. Okay, and then I multiply both sides by 3 over pi, and we'll see that theta cannot equal a multiple of 3. Okay, so everything in the domain is anything but 0, 3, 6, 9, 12, and so on, or negative 3, negative 6, negative 9. Okay. All right, so any questions there? Everybody okay with what I did? Again, I took my input on cosecant. I just first called that beta, made a substitution. I know those betas cannot be multiples of pi. And then I put my substitution back in. Beta is really what I called pi over 3 theta. Those can't be multiples of pi. And then I solve for theta. Those give me the things to avoid in the domain. All right, any questions there? All right. That was. Okay, so on the next part now, what I need to remember is that cosecant theta, whatever your input theta is, the range or the set of outputs, you're always either less than or equal to -1 or greater than or equal to +1. Okay, so for now, let me erase this right here, just to make some room. And let me show you how to find the range of this. Okay, so what you're going to first do, ignore the +4 and ignore the coefficient of 3. Okay, cosecant of some angle is always either less than or equal to -1 or greater than or equal to 1. So you have two possibilities. All right, I'll write it this way. There's two cases. Okay, the first one, we know that the cosecant pi/3 theta has to be less than or equal to -1. So any output of cosecant, so cosecant of any angle, okay, the first case or the first piece of the range says we always have to be less than or equal to -1. Okay. And then what I'm going to do is, to get this expression to appear, we're going to multiply both sides of the inequality by 3. Just a minute. We'll multiply both sides of the inequality by 3, and then we'll add 4 to both sides. Okay, so this implies, getting a little ahead of myself, this implies 3 cosecant of pi/3 theta would be less than or equal to -3. So I just multiplied by 3 on both sides. Okay, and then to get my original function expression to appear, now we add 4 to both sides. 3 cosecant pi/3 theta plus 4 has to be less than or equal to -3 plus 4, which is +1. Okay. So that'll give me one piece of the range. All the outputs of our function have to be less than or equal to 1. Okay. So essentially I ignored the vertical scaling and the vertical shifting, and we just looked at the cosecant pi/3 theta. Okay. In the one hand, that's either got to be less than or equal to -1. And then we multiplied both sides by 3 and added 4 to both sides. So the first part of the range is -infinity to +1. Okay. And then the second possibility is cosecant of some angle could also be greater than or equal to +1. So start with that. Cosecant pi/3 theta. Okay, the other piece of the range is the outputs are greater than or equal to 1. And then I'll multiply both sides by 3. And then I'll add 4 to both sides. So that'll imply 3 cosecant pi/3 theta is greater than or equal to +3. Okay. What do you have to be careful of when you multiply inequalities? So I multiplied both sides by a positive, and I kept the direction of the inequality the same. What do you have to be careful of if you multiply both sides by a negative? Yeah, you'd have to be careful and make sure you flip the sign. Okay. And then now we'll add 4 to both sides. 3 cosecant pi/3 theta plus 4 is going to be greater than or equal to 3 plus 4, which is +7. And just to distinguish it, some people put a 7 on, or a bar on their 7s. Okay. Okay. So our function is either less than or equal to 1 or greater than or equal to 7. So the range is -infinity to 1 union 7 to infinity. So essentially, to find the range, just ignore the vertical scaling and the vertical shifting. Look at the cosecant part. You set it less than or equal to -1 in one case and greater than or equal to 1 in the other. And then to get the multiple of 3 and the +4 to show up, I take this original inequality and just multiply by both sides by 3 and add 4 to both sides.
So if we didn't have the +4 at the end, the range would just be -infinity, 3,
Yep.
3, +infinity.
Yeah, right. If I just had the 3 cosecant pi/3 theta, the pi over 3 on the inside only changes the domain. The vertical scaling and shifting changes the range. But yeah, if we didn't have the positive 4, it'd be negative infinity to negative 3, union 3 to infinity. Okay. And then the plus 4 is just adding 4 to all the y values in the range. Okay. Okay, so the domain is anything but a multiple of 3, and the range is all the outputs are going to be less than or equal to 1 or greater than or equal to 7.
How'd you do the first part of the domain again?
Oh, so Claire's asking, how did I do the first part in the domain? You can do it either way. Since pi over 3 theta is my input, those inputs cannot be multiples of pi, because that's the domain of cosecant. Okay, so pi over 3 theta is my input in the, I just erased that box over here. If you looked, it said the domain of cosecant without a horizontal scaling is just anything that's not a multiple of pi. So the pi thirds theta cannot be a multiple of pi, and then I multiplied both sides by 3 over pi to solve for theta. And that leaves me with just theta not being able to be a multiple of 3.
It says k times pi for cotangent.
That's cotangent and cosecant have the same domain, if you look.
Okay, because I had it as k plus pi for cosecant.
Okay, it should be k times pi, yep. Basically, it can't, anywhere that sign is 0 is not going to be in the domain of cosecant, which is multiples of pi. Okay, good question, though. Anybody else? Clarification there? So what do you notice? The horizontal transformations are going to change what your domain is, and then the vertical scaling and shifting is going to alter your range. And then, is everybody okay with just doing for just a graphing example real quick, just to go through that one more time? Okay. Shouldn't be too pressed with time for today, so let me get this out of the way. Let me just rewrite this down here so we have it. The domain is all theta is not equal to a multiple of 3. K is an integer. And when we go graph this, you'll see that the parts that curl upward are going to have a minimum point of 7, and the parts that curl downward will have a maximum output of 1. And you'll see that all the asymptotes are going to be at multiples of 3. Okay, so anybody kind of remember the process for sketching a graph of this? Now, this isn't part of the directions, but we'll do it anyways.
We're going to graph the sign first.
It's a sign.
Yeah. Okay.
The same transformation.
Okay, so Ben and Claire, and I probably heard some other people say it too, since cosecant is the reciprocal of sine, we're going to first graph sine with the same transformations. So we first plot or first graph 3 sine pi thirds theta plus 4. And then anywhere that graph crosses its middle values where you're going to have vertical asymptotes, and then you always curl upward from a max and downward from a min. So let's go through our process here. Number 1, you can always find the phase shift first. So do we have any shifting going on for this one? Horizontal, that is.
No.
Right? You'd have to have your theta plus or minus some value, capital B. Okay, so there's no phase shift, which means our first cycle is going to start at 0. Okay, and then 2, I can always find the what? Yeah, you don't have to do these in the order I'm doing them, but I always went phase shift first. Then you find the period. It's always 2 pi over absolute value of A. That's 2 pi divided by pi thirds, which is going to give you positive 6. That's 2 pi times 3 over pi, which gives you 6. Okay. So no phase shifts. So our first cycle starts at 0, and then we're going to complete a cycle over an interval of length 6 units. Okay, number 3, you can find your amplitude. That's the distance from the middle value to a max value. Okay, Claire, you said that's going to be positive 3. So the amplitude is always the absolute value of your vertical scaling factor. That's the absolute value of 3. So the amplitude is going to be 3. And then finally, number 4 is you can use your vertical shifting to find the what I've been calling the midline. Okay, so the vertical shift always gives you the middle value. So I'll write the midline is just going to be the horizontal line y equals 4. Okay. Okay, so let's draw one cycle of this, or I guess I could draw 2 cycles, but I'll just do, well, yeah, we'll do 2. Now your minimum value or your middle value is 4, which from that you go up 3 and down 3. Okay, so your maximum value is 7 and your minimum value is 1. So I'll do this. I don't need much in the negative direction, so I'll do negative 1, 1, 2, 3, 4, 5. Oof, hold on a second, I gotta fix this. Negative 1, 1, 2, 3, 4, 5, 6, 7. And then on the horizontal axis, one cycle will be completed through 6 units, and then another cycle through 12. And I'll break each of these up into fourths, which a fourth of 6 would be increments of 1.5 units. Okay, so starting at 0, I just added 1.5 until I got to 12. That'll give me 2 cycles of the transformed sine graph. Now your middle value is going to occur at y equals 4. There's my midline. Okay. And then from there, the amplitude was 3. We'll go up 3 units to get the max value and down 3 units to get the minimum value. Okay, now since there was no phase shift, there's no reflections, okay, any cycle of sine always starts at its middle value. So at 0, you're going to be at 4 units. A quarter way through the period, you're going to go to your max value. So 1.5 is a quarter way through the period, we'll be up here at 7. Halfway through the period, you're back at the midline. Another quarter of the way through the period, you're going to be at your minimum value of minus 1. And then through one cycle or one period, you'll be back to the middle value.
Minus 1?
Yep, that's at minus 1. Because positive 1.
Okay.
I subtracted 3 to get to 1. Thank you for clarifying. So there'd be one cycle, and then I can just draw another copy. So I'll be up here at 7.5, back to the midline at 9, back to positive 1 at 10.5, and then through 2 cycles, or 2 periods, I'll be back to the midline. Okay. Now that's not the function I'm trying to graph, right? This is just an intermediate step. So I wanted to graph this transformation of cosecant. We first applied the transformations to sine. Now, here's what's interesting. When we found the domain, we know that the domain is basically, or where my vertical asymptotes are going to be, are at anything that's a multiple of 3. And that's also where this graph passes through its midline, 0, 3, 6, 9, and 12. Okay. Let me switch colors here. So here's all your vertical asymptotes. At 12, at 9, at 6, at 3, and at 0. And then cosecant, at all your maximum values, you're going to curl upward. Let me get rid of these periods here. So I'll have a piece going up there and one to the left. Okay, and then down from this minimum value, you'll curl downwards. Okay, here's another max value, you'll curl upwards there. And here's another minimum, you'll curl downwards. And there's going to be the f of theta we were trying to graph. So all the black parts. And again, does that agree with the domain and range we found originally? Okay, all my asymptotes are at multiples of 3. How about the range, right? When we found the range, we knew all the outputs were less than or equal to 1 or greater than or equal to 7. So the pieces opening upward have a minimum value of 7, and the pieces opening downward have a maximum value of positive 1. Okay. So that agrees with our domain and range that we found by hand. Okay. On a test, you can find the domain, and if I ask you to find a domain and range of a transformed cosecant or secant graph, you can do it by hand like I did at first, or couldn't I also have found the domain and range just by sketching the graph of this function? Okay, so you can, I don't care what approach you take. Okay, I personally like to do it by hand because I know I can do it faster than having to draw the graph. But if you forget how to do it by hand, you can just sketch a graph of this, figure out where your asymptotes are. Those are where you aren't going to have, those are the things you want to avoid in the domain. And then you'll be able to see what your two pieces of the range are, looking at the graph. Yeah?
Could you draw the graph from just knowing the domain range?
Yeah, I think I probably could have. Although you'd have to be a little bit careful because you have to know where the pieces are opening upward and where they're opening downward. So actually, I think you have to be careful there. You know, if you wanted to sketch the graph, you're going to know where the asymptotes are and where the, you know, what the two pieces of your range are, but you might want to be safe and apply those same transformations to sine first. I would be a little bit careful about it. Yeah, Ben?
Well, if you saw it by hand, you have the greater or equal to n or the less than or equal to n, so that kind of implies which way it opens up.
Sure. I mean, I know it's going to open upward from 7 and downward from 1.
Mm-hmm.
But did I know I'm going to, so on this first piece from 0 to 3, how do I know it's opening upward or downward?
Mm-hmm.
So I would first sketch the graph of the parent function, or their corresponding reciprocal function, and then you would know where you're opening up and down. Medea?
If there's no phase shift, it starts the normal up.
Ah, that's true. Okay, so if there's no phase shift, you know it's going to be opening upward on the first piece between the asymptotes. Okay. So yeah, there's lots of different approaches you could take, but I personally would rather be careful. And if I really wanted to sketch the graph of this, I would stick with first graphing this and then construct the graph of the original. That's a personal preference I have. All right, so any questions on this one first? Okay, we found the domain and range by hand, and then just to verify and make sure that was the correct domain and range, we went ahead and sketched a graph of this anyways, even though it wasn't part of the directions. And that's not good. We'll have to see if it's still recorded when my computer went to sleep. Okay. So one more example. Let's see, what time is it right now? 10. Okay, so we got 20 minutes. I should be able to wrap this up. So we learned our Pythagorean identity in section 4.2. And there's two more Pythagorean identities that involve the reciprocal trig functions. So Pythagorean identities.
So this is 4.5.
Nope, we're still in 4.4. It's just we're on the last page in the Pythagorean identity part. Section 4.5 is all about solving equations involving trig functions, so that's what we'll start doing tomorrow. Okay, so in 4.2 we already saw this. For all real numbers or angles theta, what was our Pythagorean identity there involving sine and cosine?
Cosine squared plus sine squared equals 1.
Okay, so, and I'm just going to rewrite it in a different order, but if you add sine squared and cosine squared, that always equals positive 1. And that works for any angle. Okay. Now, you'll see why this next one that I write down is only going to be valid for all angles theta except the ones that equal pi over 2 plus k pi. If I divide all of these three terms by cosine squared, okay, and then, so first I'm going to divide all three of these terms, or divide both sides by cosine squared. So the first term, sine squared over cosine squared. If you divide cosine squared by cosine squared, you get positive 1. And I'll get 1 over cosine squared theta on the right. Now, why couldn't my theta be pi over 2 plus k pi? Those are places where cosine equals 0. We can't divide by 0, okay? So this will work for all angles except for pi over 2 plus multiples of pi, okay? Because those values are not in the domain of cosine. Now, this isn't the actual identity, but anybody know what it might simplify to? Did you have a question?
Yes.
Yeah, what's up?
Just curious to know if the first one works for all of them.
Yep, this will work for
With
any
the second.
angle theta. Yep.
In which case, why would we bother with the other?
Why? Well, you'll see why in a second, because there's two more Pythagorean identities. The first of the two of the latter are obtained by dividing every term by cosine squared, okay, of theta. But cosine is 0 for these angles, so I can't divide by 0. Anybody kind of maybe see another way of explaining that? Yeah, Brittany?
Well, so maybe I'm jumping ahead, but won't that like simplify the secant squared?
Yep, so on the right, that'll simplify to secant squared. This is going to, since sine over cosine is tangent, that'll become tangent squared. Okay, but again, the reason why, so the first one works for all angles theta because sine and cosine are defined everywhere. As soon as I divide every term by cosine squared theta, we can't divide by 0, so I have to avoid angles where cosine equals 0, which are the pi over 2 plus k pi's. Okay, but the real identity we care about is really just rewrite this now in terms of tangent and secant. Okay, so there's a Pythagorean identity involving secant and tangent. And the reason we bother with this is just in case, if I know what secant is or tangent and I want to find the other, then we can use this identity.
So
Okay,
that's
but
the second identity that one is.
yeah. Yep, so this is the one underneath where it says for all theta except pi over 2 plus k pi, this is true. I guess you can also see it right here because the domain of tangent and secant is all thetas except pi over 2 plus k pi. And then who has an idea for the third one? So first of all, for all real numbers except theta equals multiples of pi. Okay. So instead of dividing everything by cosine squared, I could divide everything instead by, yeah, if I divide all three of those terms by sine squared, what you're going to get is 1 plus, so sine squared over sine squared is 1, cosine squared over sine squared is going to be cotangent squared. I got that from the fact that since tangent is sine over cosine, cotangent is cosine over sine. Okay, so cosine squared theta over sine squared theta is cotangent squared. And then 1 divided by sine squared ends up being cosecant squared. So you have the original Pythagorean identity plus these other two, and they're obtained by just dividing the original either by sine squared or cosine squared. Okay, so how much time do we have? Still have probably time for this, plus maybe one more extra example. Okay, so example 4. Use a Pythagorean identity, so if cotangent of 3 pi over 4, we know that's equal to -1. Okay. It's because cotangent 3 pi over 4 is cosine 3 pi over 4 over sine 3 pi over 4. If you use your unit circle and simplify, you will get -1. Anybody want to see me justify that a little bit more? Okay. So just to convince you that equals -1. So tangent sine over cosine, cotangent is just the reciprocal. So this is cosine 3 pi over 4 over sine of 3 pi over 4. And then I'll draw a picture of a unit circle. 3 pi over 4 is going to be in which quadrant? 1, 2, 3, or 4? So that'll be in quadrant 2. I'm going to also do this. So this point right here at pi over 4, the x and y coordinates are 1 over root 2. 3 pi over 4, the coordinates are just reflecting that point over here. The coordinates there are going to be, so only the x coordinate changes in sign. Okay.
You have a negative over a positive.
Yep. And now, like Ben said, cosine 3 pi over 4 is the x coordinate, minus 1 over root 2. Sine of 3 pi over 4 is the y coordinate, 1 over root 2. And minus 1 over root 2 divided by 1 over root 2 is -1. Okay, so using the fact that cotangent 3 pi over 4 equals -1, we're going to evaluate secant 3 pi over 4. And we're going to do this using a Pythagorean identity. Now, do I technically have to use the Pythagorean identity to do this? I could just use the unit circle again. Secant 3 pi over 4 is 1 over cosine 3 pi over 4, which is 1 divided by this x coordinate. So I know the answer is going to be minus root 2 if I just use the unit circle and the fact that secant is 1 over cosine. Okay, this could be evaluated by hand. I'm just doing it this way just to emphasize these identities. Okay, so if I know cotangent and I want secant, okay, which one of these identities can I use first? And actually, I might have a typo here. So if you look at the third identity, that's the only one involving cotangent. So what was my mistake? Instead of secant, we should really be evaluating cosecant. Okay, so that's just my bad. Just cross off the secant and write CSC. Right? I'm supposed to be using the Pythagorean identity that involves cotangent and cosecant. Now, cosecant squared of 3 pi fourths, using this identity down here, is going to be 1 plus cotangent squared 3 pi over 4. Okay. Now what can I do first? I can do a couple things in either order. Anybody have any suggestions?
Just replace cotangent with -1.
Okay, so Brandon said let's replace this cotangent with -1. So actually this is really going to just equal 1 plus -1 squared, which equals +2. Okay. So now that I know cosine squared 3 pi over 4 is +2, I can solve for cosecant by getting rid of the square. How do we undo a square? Take a square root. Now be careful, when you take the square root of a square, you have to make sure you write a plus or minus on the side. Now we know it's from, I already calculated this by hand, just using the unit circle. I know it's supposed to be the negative square root of 2. Okay, but how can I choose the sign based on the quadrant the angle is in? So first of all, cosecant is related to which function? Sine. And if your angle's in this quadrant, sine has a positive oh, sorry, I should have probably said positive root 2. Yeah, sine's got a positive y coordinate. Okay. So really, since sine and cosecant have the same sign, and the angle is in the second quadrant, this actually has to be positive root 2. So that's what you said, right, Claire? You said it actually had to be positive. Notice that's just the reciprocal of 1 over square root of 2. Right? I could have done this by hand. I'll be with you in a second, Brittany. So remember, cosecant 3 pi over 4 is 1 divided by sine of 3 pi over 4. And sine of 3 pi over 4 is 1 over root 2. So cosecant is just going to be the reciprocal of that, which is root 2. And then Brittany, what was your question?
I was just wondering if you would ever ask a question like that, but where we have like cotangent, if you would have us find like sine.
Yeah, I could. Yep. Yeah, I could have said if cotangent's -1, I could say find sine of 3 pi over 4.
Okay.
And then you could still use this identity to find cosecant first, and then just know that sine is just the reciprocal of this value.
Wouldn't the only way it would change it if you're trying to find for sine?
Well, so if everything was the same except for I was finding sine of 3 pi over 4, you could use this Pythagorean identity to find cosecant first, and then sine is just the reciprocal of cosecant. So it'd be 1 over root 2.
2.
Yeah, or root 2 over 2. Okay. Now, in general, I typically don't ask this question. If you already know what the angle is, just go ahead and use the unit circle. I was just doing this to emphasize the Pythagorean identity. Okay. So usually what I would say is I might say something like cotangent of an angle is something like 0.4. I might tell you where the angle is, and then I'll have you find cosecant. Anybody want, should I do an example of that real quick? Okay, so this is, if you're going to use Pythagorean identities, the question would probably more be stated in this form. So this is example 5, if we want an extra example. If, say, cotangent of theta is 0.4, and I could say where the angle is, just a minute. If the angle is between pi and 3 pi over 2, I could say find And I'll make it more interesting. I'll say find sine of theta. Now you're going to actually have to find cosecant theta first. So if you don't know what the angle is, but you know the value of one of the trig functions in where the angle is located, you're going to have to use your Pythagorean identities. The only Pythagorean identity that involves cotangent, again, is the cosecant squared theta is 1 plus cotangent squared theta. And then I could replace cotangent with the point 4. So cosecant squared would be 1 plus 0.4 squared. And is 0.4 squared 0.16?
Yeah.
Okay. Make sure this is still going. Okay, so cosecant squared theta, 0.4 squared is 0.16, plus 1 gives you 1.16. And then just like before, to undo the square, we apply a square root to both sides. So cosecant theta is plus or minus the square root of 1.16. Okay. Now sine and cosecant have the same sign because they're reciprocals of each other. They're either both positive or both negative. So if our angles between pi and 3 pi over 2, what quadrant are we in this time? We're down here in the third, where y-coordinates are always negative. So sine is negative, and therefore cosecant is negative. So we'll say cosecant theta is minus